is okay with this. Okay, you got them up? Get on the one. I prefer you download the actual app to your screen, your home screen, and use it there. But if you're going to use that web-based app, you can too. All right. Now, are you there, Tyler?
Yes, sir.
All right, now if you look in the upper right-hand corner, Lydia, you make sure that this is true what I'm telling you. Or you can help Tyler. You're going to see 3 dots, the upper right-hand corner. Do you see? 3, I mean, at least on mine, it's 3 dots in the browser. I'm not sure that was on your Lydia, right?
Yeah.
All right, and if you go there and you click on, you're going to see options. All right, now if you go to options, you're going to see auto syncing. You see that one? That's the first one, right? Then the one under that, I forgot the name, what they call that. What is it, Lydia?
The sync all files.
That's it. Click that one. You're going to turn everything on, basically, that you can. And there's one saying it says legacy panes or something like that. Keep going down.
Mm-hmm.
You see that one?
Legacy navigation thing.
Yeah, turn that on. It's going to say you need to restart, I think. Keep going down. If there's anything else, just turn it on. All right? Then you're going to have to restart. And Lydia, you can make sure Carlin can do that too, because, all right, then restart it and it should work. And Hunter, Nathaniel, you got that? You okay with it?
Yeah.
I left my laptop upstairs. I'm sorry. Did you have your laptop here? Is it working?
Not on the app, no. It's just saying,
This is the number one.
yeah, it's saying 192nd page.
No, that's, what you need to do is go.
Yeah, I didn't see any of that.
Let me shut all this. Hey, you got it.
Yeah, well, this is not complete, it's stopped updating.
There used to be like another page in that file.
This is on the website, this is the,
Do me a favor, shut all your OneNote down. I'm not gonna waste a lot of the class time, but you shut everything down. All right, now restart OneNote.
What's the most recent thing that we should be able to see?
I don't know, like Wednesday or like last Thursday, I looked. And in the chapter 10 folder, there was like 2 files.
I can see the chapter 10 notes and
But
home.
like the second file is
How
no
far
longer
do the
there.
chapter 10 notes go?
They go all the way down to, they just have 2 Smith charts at the end.
Save.
Yeah,
Okay, yeah, that's not.
yeah, no, it's saying.
Okay, well, I'll quote it and, I am getting an error with this sync. It says saved offline. Sync error. Can't sync this page.
Yeah, that's.
Oh, now it's deleted.
Can you shut down your computer and restart it?
I'll open it on the Finder, the browser.
Yeah, mine says,
Yeah, yours, right?
Yeah, but I think mine did that afterwards too.
but mine even says it like on the app on my iPad. So it says, no, can't sync this page, put it on the page for short-term fix the issues. It says that I'm working on line and error, but I'm not.
Go back to the, just go
Now the chapter 2 notes are deleted.
and go to, see if you can see some of the other stuff.
Well, those are old, so you can see those. I can see old stuff. The problem is that we can't see anything new.
Hit the
that's
chapter
different.
10 notes, hit chapter 10.
Well, this is mine because I posted the notes, but no one can, they can't see what I posted.
Did someone delete
Well,
the
that's
chapter
not
10
your-
notes just now?
Yeah, I don't know what happened.
No,
They- I think they just got deleted.
I can't put on, it
Yep.
Does yours say sync in the top left corner?
Remember?
Or does it say saved offline?
says working offline.
Working offline? Can you click that and see what it says?
Here, you got yours, give mine up.
Yeah, it's screwed back
Yeah,
up.
see, they're supposed to, oh wait, keep going. Yeah, so they're supposed to be more after that.
I think it is.
You have to find the
Details says
options.
OneNote can't see this way.
they're syncing. We just need hers to sync to see the note.
And go to, the options and wherever it is.
I think we just need hers because I think hers.
Well, I'm worried that because we're not going to do that either.
There's like the same.
We're not going to know.
It
who
says,
posted
he
either.
has
He needs to
says this on that.
Like earlier this morning, I just
If he
deleted the app and redid the app and re-signed on everything.
That, yeah.
But, I mean, if we can't see his files, then everyone can see his files. Like, the problem would be is like if one person couldn't see the files. Like one person, in particular, like that would just mess them up.
Right, see his file?
Yeah, but I think we can see his files.
Yeah, that's what I'm saying, it's like, if we can see his files, then we're good, we just could use her notes to do the group meeting.
Only thing is, I don't understand like why that would just be an issue now.
Can you-
Like if that was the problem, we would.
Can you go through the canvas and try to open the OneNote in the browser?
Yeah, I can try to do that.
I think that might fix it.
That's what I just did.
Yeah.
Okay.
It didn't
Well,
work.
I'll tell you one other thing too. With all these softwares that are online, they update them. And it may not, I've had this problem where Microsoft updated something and it wasn't a seamless transition. I had to go to like Windows 365 and when I had whatever the other version of Windows was, Windows 10 on there, it wouldn't work. Now, I don't know if it's because of,
Maybe you just had to sign back in.
that there's a conflict.
The only real problem,
What, it should be in the announcements on Canvas or something? I can also, I'll just send you the link to it in the group chat, group me.
we wouldn't know you posted it, whereas like we talk to her regularly and do group message. So if you can just.
I didn't post the link.
Yeah, but like if you can
Yeah,
post
it's
it,
no-
you get the
Are you sure?
file.
I thought someone deleted.
I'll make that sure.
I just put the link to OneNote in the group name. Click on that and see if it comes up.
Says that like chapter 10, there's like no notes.
Yeah, it's deleted for us too, but does it say sync now?
Sync where-
Like any.
You get it?
Yeah.
Is it working?
Yeah, so it's synced
All right, he's
Can you
got it.
post your notes?
Well,
Can
she
you mark it
said
up?
there's one.
But go down, and then it should be class notes and should say, I hope. Listen, I don't mean to take this much time on this, but this kind of thing can irritate students to no end. Because I'm gonna post stuff and you're not gonna have access to it. I can go over the quiz real quick if you want to do them as well. It was a straightforward quiz, but there were mistakes there when we're going through it. And somehow I had written down an L of 3.5 nanohenries, and somebody changed it to 3.47. I didn't understand what was going on. I mean, I just tell you, I'm not sure what was going on. So let me go through this quiz. This is a straightforward quiz, and it's S parameters. Now, I'm not going to give you, we're down with 3, 4, 4, 4. I'm going to give you some 3, 4 parameters. Wait a second, didn't I give you 3, 4 parameters? Or just 2, 4? I did give you 2, 4, right?
I believe so.
All right, so you're done. You had 3, 4. I'm not gonna give you a 4, 4. But you basically understand how to go through and analyze the import system. So this one was a standard type thing where I had an inductor here, L, and that was equal to 3.5 nanometers. I had a frequency of 10 to the 9th hertz. And then I had transmission lines of 50 ohms on either side. And I just want the S parameters for this, right? So, I wish I would have had the whole thing done. So the first thing I'm going to do is get the inductive reactance, and ZL is equal to J omega L, and omega is equal to 2 pi F, which would be 2 pi times 10 to the 9th hertz. That would be in radians per second. So this, I believe, is J24 about, can somebody just tell me that?
It was,
If you-
in the homework, it was 21.99.
No, I
think.
It was the same problem. Or,
21?
Twenty-two.
Two. Anybody else? J 22 homes, okay? So that's ZL, right? Now the next thing we have to get is ZN. Right here. So ZN would be equal to this impedance right here, which is gonna be ZL, plus Z naught of plus 50. And I don't know exactly what that is, but it's just 50 plus J22. Now, when we get the reflection coefficient, that's the impedance you're going into, minus the impedance you came from, over the impedance you're going into, plus the impedance you came from. And so that's going to be this minus 50, or it's just J22, right? Over Zn plus Z naught, which is 50 plus J22 plus 50. And I want to say that's 0.21, but I don't remember exactly, at about 33 degrees. Is that one? Help me with that, guys. You guys have your calculators. This is going to be 100 plus J22 divided into J22. I need a magnitude of the angle.
.215 at an angle of 77.59.
That's right. 77.59? Yeah, that's right. So that's the reflection coefficient. And what's the transmission coefficient going to be? 1 plus the reflection coefficient. It's just a hair over 112 degrees, I think. Can somebody just take that reflection coefficient, add it to 1, and give me the magnitude negative?
1.07 at an angle of 11.34.
Yeah, that's right. So with that, we got the input impedance, we get the reflection coefficient, we have the transmission coefficient. The first thing we get is S11, and that's minus 20 times the log, that's a base 10 log, of the magnitude, let me get S11. S11 was doing the insertion loss. S11 itself is just equal to the reflection coefficient, and it's the same for S22 because this is symmetric. These ports look the same no matter which way. And for this one, it's going to be that value, 0.21 at an angle of 77.59 degrees. Now, when we talk about S12, it'll be the same as S21. And that's going to be, first I have to take the transmission coefficient tau. You all understand why, right? Because technically this is fun. This would be like V2 minus over V1 plus. So when V1 plus is coming in on port 1, I multiply it by the transmission coefficient first. Now I have the voltage on the other side. And then I multiply it by voltage division, which is Z naught over Z naught plus, I can put down J omega L and just put, what do they call it? ZL here. All right, so for this, what do you get? It's the transmission coefficient plus, or times 50 over 50 plus, whatever that is, J22.
I got 0.977 to the angle of -12.
That sounds right. About minus 12 degrees?
Yeah.
Y'all with me? All right, so that's that's S12 and S21, right? And they're the same. So basically, as soon as you get S11 and S21 or S12, you have the others. So because of some, then you get the insertion loss, and that's minus 20 times the log base 10 of the magnitude of S11. And then you get the return, that's return loss. That's return loss. Then the insertion loss is equal to minus 20 times the log base 10 of the magnitude of S21. Or it can be S1 too, they're the same. Now, what do you get for the return loss?
13.36 dB.
360 dB?
Yes.
And what's the insertion loss?
0.211 dB.
And that's how it goes. This was not meant in any way, shape, or form to be difficult. It's just to make sure that you actually understood the concepts. The biggest problem always is, in my opinion, this right here. People forget the transmission coefficient. Anyway, that's the solution now. Now, other questions before I go? I'm not going to do, if you look in there, he does a whole section on filters. And there's Butterworth, Chevy-Chef, all these things. Do you have a course in filter design or something like in your circuits courses that does filters or?
In RF systems, in
Yeah.
that lab, we have to do filters.
All right. I just want to tell you one thing. When I was in grad school, I had an advanced course in design and synthesizing filters. Usually filters, for the most part, you analyze them as undergrads. You don't synthesize. Well, grad school, you synthesize, and there's Callier 1 filters, Callier 2, has to do with their series, parallel types, LC type things. There's Chevy-Chef, there's Butterworth filters, there's a whole spiel of filters. In this day and age, if you want a filter to do something, you have to understand the basics. Most of you understand high pass, low pass, band pass, band stop, right? Now there's a thing called Q. You remember with Q? The higher the Q, the sharper the filter response, but the higher the Q, the more overshoot right at those transitional frequencies. Those are the two things. I'm not sure if I really want to, I normally don't delve into that because this is more, he has it in the microwave section. This is really a circuits type of, you might say, technique. In the circuit analysis, you get a lot of this stuff. But in microwave design, you're really worried about matching things, beats matching, line lengths, things like that, S parameters. So I'm going to forego that. Now, unless you want me to, and I'll be happy to do it if you really want me to. I'll do all the Butterworth and Chevy-Chef and a whole lot of parts on that. But to be frank about it, a lot of it is just cookbook stuff. It's not very innovative. And to be frank, you know how that tool I gave you for L section matching is online? You want filter design in this day and age? There's so many free tools. You just tell them how many dB of attenuation you want over a certain range of frequencies. You can literally sketch out the filter you want and it'll, boom, come up with either passive or active filter for you. I do want to say one thing too about filters. I'm not an expert in super high frequency filters, but anytime you're over about a gigahertz, everything doesn't look like it should. A resistor, just because of the lead lengths, it looks like it's got inductance. A capacitor looks like it has inductance. There's all sorts of parasitic things, inductance and capacitance, that cause high frequency behavior in filters to be much different than low frequency. So you have to be very aware of that. And even sticking your hand to the actual circuitry, just the sticking your hand in causes a change in capacitance that you'll see the frequency, center frequency will move. So that's how sensitive high frequency circuits are. Just in case you start dabbling, and you probably will. The reason where I learned about that, and I'm just sort of trying to give you a perspective here. When I was in grad school, we took a CB radio and turned it into a ham radio. I don't know if that's legal or not, but we were allowed to do it. Well, CB is cheap, right? It's 5 watts maximum. Ham radios can be very expensive. So we had to change the frequency band. That meant the crystal oscillators and all that stuff. Now the amplifiers pretty much weren't that sensitive to changing frequency. But I remember what an incredible pain it was to tune these things, because they have little inductors that are in these metal casing. They're real small, about like a, if you know it's basically the size of your thumb. It's a metal box and it has a little thing on top where there's a screw that you can adjust. We can use dielectric screwdrivers. And if we put our hand in there, if we didn't have a long enough one, it would start changing the actual frequency that it's operating on. We have spectrum analyzers, I remember. We have a center frequency. We need the frequency to drop down because as you're tuning this, you have to have exact frequency. It was the biggest pain in the butt I've ever imagined. I'll never do that again. So with high frequency engineering, remember, everything is super sensitive to the environment around and for filter design studies. Now, what I'd like to do is cover two things in a little more depth. I gave you the thing about EMC in more detail, right? You remember the waveforms? We have a rise time, fall time, then we have an on time and T, and I showed you how the actual frequency response was, right? You got a certain plateau, 20 times the log, really duty cycle times the magnitude of the pulse generator, right? Divided by 10 to the minus 6 for microvolts, dB microvolts. Then the thing went, there was the first break frequency, 1 over tau times, really, if you remember doing this, it was 1 over pi tau, tau was the on time, and then it would go down 20 dB per decade from then on, and then when it hits the second break frequency, which is 1 over pi tau rise, then it starts falling down 40 dB per decade. That's not in the book, but I think it's very relative and important in your analysis when you do EMC stuff. That's the bandwidth stuff he puts in there just doesn't fly. This is what I showed you to do. It gives you the real values. I'd like to do something with radar, because some of you, especially in this day and age, it's hard for me to believe that not a chunk of this class is going to be out there dealing with some sort of either data transmission or radar analysis system out there that's going to be looking at echo returns and doing data processing. Nowadays, cars, I don't know if you realize this, but most new cars that I know of have radar, they have collision avoidance radar, they have terrain mapping radars, and I want to go through a little more depth about that radar, if you don't mind. Now, again, this is, if you want me to change and do filters, I'll just be happy as a clam to do that, but I think this would be more valuable to you, okay? And I have my clue because I've covered everything I need. So here we go with radar. Now, anybody teaches this course, and I do research. So with a standard radar, what you learned was here, and this is a standard radar. This is an antenna, obviously. And the antenna has a certain gain. GT is the gain of the transmitter. There's also GR, and that's the gain of the receiver. There's going to be a certain amount of power transmitted. For now, you might as well assume this is just peak power. The radar is going to send a signal out, and there's going to be a target at a distance R. We start really simple. When we talk about a target, now that's sort of a catch-all. It can be something you don't want to get. That's called clutter, like when you blast the ground with radar and gives you a return. You don't really care for that. But it's still a target. And a target can be something you want to find out its distance or its velocity. So for this target, it's given the size of this is the radar cross section. And the symbol we use for that is sigma. The units are meters squared. So that's the size of the target. Now, how many remember doing this? This is a good review. You're going to get it on the final, so starting here's a good start. But what I really want is if I transmit a signal, I would like to find how much of the power I transmit is reflected back. That's the first thing. You with me? So we've done this before. So we want to get the power received. Receive at radar. All right, so P receive, does anybody remember how to get that? This is, I like people to think this way. It'll save you a lot of heartache and pain. First, you take the total transmitted power. Just put it down. You know the power received has got to be proportional to transmitted power. Next, when you transmit that power, it spreads out as 1/4 pi r². That's the surface area of a sphere. Y'all follow me? So this is if there was no antenna, we're somehow able to blast things away with no focusing ability. That would be the power density that's being launched out there. But then the gain of the antenna, the transmitter gain helps focus the beam, sharpen it. It increases the power density at certain points in the main beam. So it's the gain of the transmitter. Are you with me, everyone? We'll make sure to walk you through it. Now I've got that power density, and if I know wherever the target is, the aspect angle and stuff, the gain will be a function of angles. I can adjust that. But now there's a certain amount of power that this thing is going to reflect back at me. Y'all with me? That's the power density on target. So that would be multiplied by the radar cross-section sigma. Now I've got, that was watts per meter squared before I put sigma there. When I multiply that times meter squared times sigma, now I have watts. Y'all follow me on that? Now all that's scattering back, right? And it's going to scatter back as 4 pi r² as well. I'm going to simplify this, but you all understand this. Now, here's something to take note of. Gain is in general a function of angle. So there's a thing called the bore site of an antenna. That's where the maximum gain is. And as you come off the bore site, in terms of the angular difference, then the gain will be reduced. So gain itself will be a function of angle. But for now, we're going to assume gain is maximum gain that's in the bore site. With me? This radar cross-section sigma will also be a function of angle. And what they do is adjust sigma so that if my transmitter is coming in at a certain angle of the thing, but the angle, the actual information I want collected is at another point, it's called a bistatic radar, then that sigma will have a different value. You're going to have to just understand. Think of it this way. If I have a mirror here, and you're where Nathaniel is in the back, and he shines a light at me, right? Nathaniel can see the reflection perfectly, right? But off to the side here, where Han is, he's going to see a lesser value. He's not going to see the full intensity. And the best way to think about it is if you have like a mirrored surface that's in a sphere or something like this. Y'all with me on this? So radar cross-section also, that's the power density you're going to feel back at the antenna. PT times gain over 4 pi r² is power density on target, times the size of the target. Now that's the amount of power that will be reflected. When I divide that by 4 pi r², now I have the power density here. You with me? Now I have to catch that power density. And that's going to be with the aperture of the antenna. Well, the aperture and gain are interrelated. Does anyone remember what aperture is in terms of gain? They're directly proportional, right? It'll be the gain of the receiving antenna, but there's one thing that enters in. Do you remember what it is? It's lambda squared, right, over 4 pi. And this, what I just put down, is the actual size, the area of the antenna, how elliptically big it is. It's the aperture of the antenna. Y'all with me? How many remember that? Or at least it's bringing you back. And now I'm going to take all this stuff and I'm going to condense it into what's usually termed the radar range equation. It's the most general form of the radar equation. It's transmitted power, gain of transmitter, gain of receiver, times sigma times lambda squared. It's divided by 4 pi cubed, that's just a constant. It's proportional to r to the 4th, and that's it. And that's how much power you're going to receive back if you transmit a certain amount of power. And I hope this makes sense. Now, can you read it, Carl?
Who's that? RRE? on the top.
Radar range equation, sorry. It's just, that's how it's termed, RRA, the radar range equation. So that's how much power is received if you know the power transmitted. Now, when we talk about a radar signal, there's several things you have to understand. A radar signal usually isn't just on. It's not a constant power. What they do is, they take a baseband signal, just listen to me, don't lie. So they're gonna take a signal, a low frequency signal like this. And this thing will have a certain on time tau. It'll have a certain period T, and T is called a pulse repetition interval. Or the PRI. Frankly, T I like better. It's usually the period is what we talk about. We use capital T for that. We talk about the duty cycle is simply tau over T or tau over the PRI. This is just terminology at this point. Now, this is going to have some value, and I'll just call it V naught there, and this is V of T. Now, this is called a baseband radar signal. So I'll just say this is called a baseband. What that is this is the low frequency modulation method we're going to use. We're going to take this waveform and multiply it by carrier frequency and then transmit it. Now, you all remember AM modulation, right? And you remember FM. AM was what? You took some low frequency signal and you multiply it by a high frequency signal, and there would be an envelope, a low frequency envelope, but all the high frequencies were inside that, right? You all remember that? Same thing here. This is amplitude modulation. So that's the baseband signal, and I'm going to call it just V of T here. And when we take a look at the transmitted signal, I'm going to erase this for a second. Here's what we get. Wednesday's the last class, isn't it? We don't have Friday, do we? Before I forget to do this, Leah mentioned you may want a study session, like not this week, but next week. Is that because our test is on Friday? Right? Now, I don't know if, I don't think I have the authority to dedicate a room, but I can do it on Zoom if you're okay with it. If I can get this room, I'll get it, but the problem is they have finals going on. And if I just say, well, we'll have a room at this time, the scheduling goes to the registrar's office. And a lot of times, I don't even know if I have access to some of that information, but I'm just going to tell you, I don't know if this room's going to be or used or not, but I surely can do it on Zoom. Is that all right with you guys? How about you guys get on GroupMe? You can run this, William, or Lydia, one of the two of you. Why don't you do it? Find out what time's best for everybody next week and then let me know. Try to do it in the afternoon after about 1 o'clock. Because I get sucked into a lot of meetings. I get the 3:30 meetings and I get the early meetings around 8 to 10. So I'm just trying to tell you, I'm pretty sure if you can get me after 1 in the afternoon, I'll be available, okay? Let me know. All right, now, that's VT. So when we actually transmit, here's what happens. We take V of T and then we multiply this, the multiplier circuit you don't need to know about, with a high frequency signal. Typically it's cosine of 2 pi f naught times T plus some phase angle. And this is the high frequency carrier. So what comes out of here goes through, then it goes through a power amplifier. I'm doing this in a block diagram approach because a lot of this that I'm showing you, this would be caused by, oh boy, there's a lot. magnetrons / klystrons. I could just tell you one thing, or cyclotrons. I mean, there's a lot more to this than I'm showing, but generally they do block diagram approach because you're familiar with amplitude modulation. You take an incoming signal via T, a low frequency baseband signal, multiply it by a high frequency, what comes out? Well, that's V of T, that's right here, times cosine of 2 pi F naught T plus the phase angle. Then you're going to amplify, and then this goes right to your antenna for transmission. And then it's launched. It comes back. Y'all with me? This is a transmitter portion. Should make sense to everybody, because you've had AM, amplitude modulation. Now, if you look at that, the actual transmitted signal right here, I'll just call that V transmitted, and really it can be the voltage on the antenna. It doesn't have to be the power density. But what that looks like is this. It's going to have this envelope, the low frequency envelope, but then it's going to have actually better be power. I'll call this the P of P. The transmitted power itself. What it looks like is a very high frequency waveform that's got a square wave envelope. Go with me? This is still tau. This is still capital P or the PRI. I should make one other note. Whenever you read stuff about radar or talk about radar, oftentimes they talk about the pulse repetition frequency, which is 1 over PRI. Just think of it this way. 1 over 60 is the actual period of the wall voltage. But normally when we talk about wall voltage, we talk about 60 hertz. Do y'all follow me on this class? Same way here. They talk about PRF the way we talk about 60 hertz. And PRF, the pulse repetition frequency, is really maybe kilohertz to hundreds of kilohertz. Sometimes it gets into megahertz, but you're going to see one that comes from. So this is just a transmitter portion of the antenna circuitry. And that's what comes out the antenna, very high frequency, amplitude modulated waveform. So we send that thing out, and now we have to think about things logically. Just think about this for a second. Let me erase this. And I want you to listen to me on this one, because I want to make sure you see it. I have an antenna, and I'm launching a signal. Here's what it looks like in baseband. Right, this will be my V of T. Right? This is tau. This would be capital P or the PRI. This is the signal that's being launched from there. Well, it's going to come out. It's going to hit something in a range R. The signal's going to hit. It's going to come back to the antenna. Now, if we were to look at a graph of the transmitted here versus, and I'm going to just show you, it looks like this. Then V received would look like this. It would be nothing until I hit a certain point. And when it basically shift this entire waveform by a certain amount of time, right? So this would be the delay time. I'll just call it TD. Y'all with me? Doesn't matter the symbols. Well, what is that delay time? This is important. So the delay time, and I better call it that. How would we get that? You're smart people here. You know that this thing's propagating at the speed of light, right? Y'all with me? So if it's propagating at the speed of light, the distance it travels would be c, the speed of light, times time, right? Well, how far does it have to travel? It has to hit the target and come back, so it travels 2r. You with me? So if we take that distance, 2r, and divide it by c, we get this time delay. So if we take 2r divided by C, that's the time delay. You all see that? Should make perfect sense. Right? You send a pulse, you listen, bang, it comes back, the leading edge, yeah. I can figure out how far away that echo came from, you know. But as you're looking at this, there should be something that bugs you. What happens if the delay puts it out here? Y'all follow me? Suppose instead of this being the delay, suppose that now I send a pulse here, and the first time it comes back is out here. Now that means the target will lose a lot further away. Y'all follow me? But what's the problem with that? You don't know this one caused it or this one caused it. That's called an ambiguity. So there's a range, maximum ambiguous range that we talk about. And that range is found this way. If we, before we can ever send another pulse, right? We're assuming a target's maximum delay is not going to be beyond this point. Because if it is, then we can't tell which pulse caused it. Does that make sense? So there's a thing called a maximum non-ambiguous or unambiguous range. And this is maximum unambiguous range. And the symbol is RU, and that maximum unambiguous range is going to be C times T, or the PRI, divided by 2. C times the PRI over 2, or C divided by 2 PRF. Now that should make intuitive sense to you, right? This is the truth. Now that's how far away I can see stuff. So here's the deal. Usually when you're building a radar and trying to do detection, you figure out, well, what's the furthest target I care about in its size? All right. So then I can either design this pulse repetition interval, right? If I know how far, the maximum thing I care about a target, then I can design this pulse repetition interval. Now the other thing is this. I know that as I send out energy and it hits and comes back, it's falling off this 1 over r to the 4th. Y'all follow me? So if you think about a target being 1 meter away, the amount of power would be proportional to 1 over 1 to the 4th. But if it's 10 meters away, just think about this, it's 1 over 10 to the 4th, right? Or 10 to the minus 4th, right? If it's 100 meters away, it's 1 over 100 to the 4th, or really 1 over, and it would be what? 10 to the 4th, 1 over 10 to the 8th, or 10 to the minus 8. Only, and you can see the rapid orders of magnitude. Now, what they normally do is they say the largest possible target I'm ever going to run into is this big. I have to make sure that the return from this thing, no matter how far away it is so low that the signal is not going to really matter in terms of the actual analysis. So that's how they normally set the maximum non-ambiguous range for most targeting. Now there's other factors, but that's the general rule. You want to make sure you don't go so fast that near targets you won't be able to discern what range they're at. That's the maximum non-ambiguous range. There's another thing that happens with radar, and that is something called range resolution. I'm going to try to make sure you see it. All right. I think you understand that if I have a radar here, and I'm transmitting a signal, my target's out here, right? And this thing's at a range R here. Well, what happens if there's 2 targets like this? Both in the bore site. One of the things you're going to have in your mind is, well, this target won't be seen because this thing's hiding. No, that's not the truth. With radar and stuff like this, that signal gets around small craft and stuff like this. You don't have to worry about it. But anyway, there's going to be a distance where I'll be able to differentiate one plane from another. Do y'all follow me? Now, I want you to just think about this logically. I send a pulse like this. I mean, let me try to make it bigger. This is what I'm sending. This is the baseband we always worry about. So this is a transmitted pulse, right? Then I'm receiving a pulse back, right? Just think about it. So here's my first target, receive back. I'm going to say it comes here. Now, what if there's another target just a little further away? Then I'd get that, but I'd also get this. Now, this time right here is tau. I'm not worried about the time delay or anything. Y'all see that? Can you all see how these things are overlapped, right? And there comes a time, what's called the range resolution. Well, these things have to be a certain distance apart to see two distinctly different things. Otherwise, you just get a signal that you can't differentiate which target caused the echo. It looks like a long target. So this is called the range resolution. And the symbol is delta R. It's a similar formula. It's going to be speed of light, but then it's delta t, or sorry, speed of light times tau over 2. Now, we could go through this, but I send a pulse, it comes back, right? The time delay, if you think about it, would be, if it's at a certain distance away, it'll be, this would be the time delay TD, right? And then, however far this target is away, it would be C delta T over 2 further. Does that make sense to everybody? So this target is actually going to be T delay plus C times tau over 2. And until C tau over 2, C delta R, 2 delta R is equal to C tau over 2. You won't be able to see that second target. This is called a range resolution. Just think about it. The shorter the pulse here, the smaller the range resolution. You can resolve targets. If there are two planes flying and they're only 100 meters apart, if tau meets that condition, you could resolve it if the range resolution was less than 100 meters. But it's real important to do this. And have you ever noticed how with aircraft, they fly in a V wing usually in the military if they're going to do anything? The reason is you don't know how many planes are out there. When you're a radar operator and getting a return, you see all these things at the same point. You don't know if it's one plane or a squadron of F-15s. You have no idea. That's one of the things about this radar resolution. It becomes very important. Some people will say, well, when I look, I can tell there's one. You don't understand with radar. The only thing you see is a glimmer, you might say. Think about things miles and miles and miles away where you might see a glimmer from the sun. With radar, you basically see a return that gives you no features about anything out there. Generally speaking, the only thing is you're going to get a return strength and you know the relative strength of the return. But that's about it. It's very hard to figure out anything more about the target. So that's the range resolution. Y'all with me? Now, there's one other thing that should make sense to you. You know, when I'm transmitting, if this is the transmitted voltage, right? The transmitted power should follow that, right? Follow that? So then we talk about there's an average power and a peak power. With radar, if we take a look at the power signature, and this is just transmitted power, and I'm going to assume we're going to have an average power here during the on time, and then it's off. It's on and it's off. This is tau. This is going to be capital T or the PRI. And therefore, the average power, or P average, would be equal to the peak power I'm just gonna label that as peak power. Times the duty cycle, tau over T. Now that should make intuitive sense to you. You know what average power is, right? You know what average anything is. It means you find the value it's at when it's on and multiply it by the duty cycle. Y'all with me? We're gonna see that that becomes an important factor. I'm gonna stop there. I'll give you some basic stuff about radar. I didn't cover the Doppler here, but you've had Doppler frequency, if you remember that, right? You can look that up. I'm gonna give you several problems. Then on Wednesday, what I'm gonna do is take this and try to complete the thought so that you'll have a better appreciation for real radar processing. Now, I'm not gonna try to extend this and make this a difficult portion. I'm just trying to give you a peek at what's important down. Yeah.
When you're receiving the power,
Which
you
one?
have the, so when you're receiving the power from the antenna, from your object that you detect.
Right.
How are you separating that signal, like returning, because you have the transmitter going to your antenna, how do you
This is
receive
beautiful.
that?
This is a wonderful question. Remember one thing I said, when I'm transmitting, right? Up to this point, anything I receive back, I won't be able to see. It's called eclipsing. This is a very important point. This is why these duty cycles are typically tenths of a second, or tenths of a cycle. So it's only on for 10% of the time, maybe 5%. And the thing is, if you're transmitting, you can't hear if it's the same antenna, right? So normally they have a transceiver switch. It transmits, it's assuming anything out there at this short range, it would be C tau over 2. You don't care about it, or other radars pick it up. When it starts transmitting, usually this is much longer, all right? It starts transmitting. Instantly, when you have a TR switch, it goes from transmit mode, from power, switches to the receiver. So there's a thing called a transmit receive unit or a transceiver. It just turns on, off, on, off, on, off. It's almost like an old walkie-talkie. You know what a walkie-talkie is, people? You would push down and you talk. You couldn't hear anything when you were talking. Then when you let go, you would listen. It's the same thing with radar. You transmit, you can't hear when you're transmitting, then you listen. That's for typical monostatic radar. Now with bistatic radars and some of the advanced radars, they can transmit and listen at the same time. The problem is they have to isolate. There can be none of this signal bleeding directly into this antenna. And that's a much harder problem, but they do it. It's more difficult than you can imagine. But anyway, okay, I'll give you some homework. I'll see you Wednesday. And somebody asked me about a wrap up for Image 1. So I can do some of that on Wednesday if you have questions about what Image 1 you're responsible for. You want to, here, I'll just give you the bottom one. Capacitors and inductors. You're going to have to figure out capacitance for the system, inductance, standard. And I'll go through it. Go ahead and Daniel.
What's the best way to study for the fun? What impression do you have?
Well, now it depends, everybody, where's your weak areas? Me personally, going through the homework, stuff you know how to do, move past, you gotta make sure you know how to do it. Work on the stuff you have trouble with or causes confusion, because the final comprehends, but it will have S parameters, it'll be weighted more towards the material you have it had on first exam. So you're gonna get S parameters, you're gonna get L systems, L matching networks. You're gonna get stuff like you get some EMC, right? You're gonna get that crazy waveform thing where it's rise time, hold time, right? Where you have that. But I always recommend do the homework. If you talk to people that have had me before, and Carlin, I think you'll find out they'll tell you that generally speaking, you can look at my old exams if you want. They're all out there. There's old finals, I'm sure, all over the place. Generally speaking, that's not the best advice you can get. It's do the homework and look at all the quizzes and the homework I've assigned, and that's where the money is. I'm not gonna give you something bizarre like Riggs does. I know Dr. Riggs comes up with stuff that's like, I don't know, it's out of Twilight Zone, ask you. We covered this and he's asking us to solve this problem. I don't do that. Okay, one more class. Hey, Ken, do the review.